Okay, welcome back. We are going to talk about series today. We're trying to figure out if I add up a bunch of terms of a sequence, if the sum actually goes to a number, or if it diverges. And if it diverges, it could get bigger and bigger and bigger. It could get smaller and smaller and smaller, meaning it could run off to infinity or negative infinity, or it could just bounce back and forth, right, and not actually go to a number. So those are some possibilities. If it does converge, then we want to try to figure out what it converges to. So what we want to do is put a number right in here like a t and say, take the limit as t goes to infinity of the sum of a bunch of terms in a series. Or if you prefer, a bunch of terms in a sequence, right? A sequence is a list of terms. A series is going to be the sum of those terms in the sequence. So what we know so far is we should take a look at these and see what happens. Clearly, if the terms themselves are getting bigger and bigger and bigger and bigger, and I'm adding them up, then this is going to go off to infinity and diverge. So for a series to converge, the terms themselves have to be going to zero. So we could look at this sequence of terms and say, are they getting smaller and smaller and smaller? If they are, it has a chance to converge. And then we would have to look at it a little bit closer and see if it actually does. So all of this stuff for me would be a little bit of investigation in Desmos to try to see what's going on. Of course, you could just use your calculator and your pencil, but it takes longer. So I'm going to flip over to Desmos and use that because that's pretty much how I would start. Today, I didn't have anything preloaded for you. So even if you're showing up to your exam with nothing ready to go, it still doesn't take that long to type this stuff in. So what we're going to do is we're going to say, I have a sequence of numbers, okay, which is a function with a positive integer domain. And we're going to say it's 2 raised to the 2n power times 3 raised to the 1 minus. Oops, it doesn't like minuses. So how about 1 minus n power? How about that? I'll fake it out. Okay, so it looks to me like the terms of, and then I don't know if it's freaking out here or not, so maybe I'll just put a multiply in there just to make sure. It looks to me like if I graph this, I'm graphing a real valued function. And so Desmos defaults to n is any real number. So if you want it to be just integers, then you're going to plug in just natural numbers. I like to use big N for the natural numbers. Desmos can't do infinitely many of them, but it can certainly make a list of the first 100. Okay, so then what would we do? We would stick in the first 100 numbers and into a sub n, and we would look at where they go. Of course, there's the dots. So it looks to me like these are getting bigger and bigger and bigger, which means the terms themselves are getting bigger and bigger and bigger. So it sounds to me like it's going to diverge. Right? If you'd like to look at the sums, then what we want to do is look at the partial sums. So we're going to say the sum of the first n values is equal to the sum, and I have to use a different letter here, I equals 1 to wherever we go, and we're going to go to n of a sub n. In other words, we're going to add up the first n terms of our sequence to get the nth partial sum. And again, look at these purple lines. It's saying, oh man, I think you're putting in real numbers, right? We don't want to put in all the real numbers. So what we really want to see is just the dots. So we'll put in just the first 100 integers. And there's our sums. Let's see, I'm going to make the sums red and the terms green. And so you can see that the terms are getting bigger and bigger. The sums are getting bigger and bigger. This looks like it's running off to infinity. I say diverges. Okay, so another way that we might check on these is we might say, I know a few series. Okay, I've already studied a few series. In fact, the most important series that we've studied is called the geometric series. And we know that if a series is geometric and the ratio is less than 1, then the series is going to converge. In fact, we have a formula for what it converges to. So we can even tell what it's going to converge to. So you might say, well, this looks like something to a power. This is looking like it might be a geometric series. And so the other thing we might do is just rearrange this so that it looks a little bit more like a geometric series so that we're sure that it is. So do a little algebra. Let's see, do a little algebra. All right, well, how about we start with this? How about we just pull this part apart and we say, this is the sum, n equals 1 to infinity, of 2 to the 2n times 3 to the minus n. Because of course, when you multiply with the same base, you add the exponents. Okay, so that looks like it might be the sum, n equals 1 to infinity, of 3 times, and of course you could have factored this 3 all the way to the front, of 2 to the 2n over 3 to the n, because we have a negative exponent. When you have power to a power, right, you multiply. So I can rewrite the inside part as 2 squared to the n. And of course, 2 squared is 4. So I'm going to write this as the sum, n equals 1 to infinity, of 3 times 4 over 3 to the nth power. So it looks to me like now it's definitely in the form of a geometric series. So this one is geometric, right? Geometric series are defined as you take the last term and you multiply by a common ratio. And of course, the common ratio is 4/3. So what am I doing? I'm making the next term 4/3 the size of the previous term. Okay, well, that doesn't sound so good. 4/3 means bigger and bigger and bigger and bigger. And of course, this thing runs off to infinity. We could say that our ratio, right? Our ratio is greater than 1, so diverges. And you might have to say geometric if you want to be clear. Geometric with ratio greater than 1, so diverges. Okay, and that would be a proof, right, if you will. Although the evidence in Desmos was pretty strong. It was indicating it was going to run off to infinity. Okay, so one of the things that we might do to see if a series converges is check to see if it's a geometric series, because if it is, then we know what it does. But not every series is geometric, right? So we started out a few days ago, we kind of introduced series. We didn't look at any particular kind, we just looked at all different kinds. Then on, when? I don't know, Monday, I guess, we spent some time looking at just geometric series, so specifically zeroing in on those kind. And now we're going to be a little bit more general again and say, all right, well, if it's geometric, great, they're easy. But what about all the ones that are not geometric? What do we do with those? And so we'd like to look at a few more techniques for figuring out what to do if it's not geometric. And that's what's going on today. Okay, questions? All right, see you none. Check out number 2. Number 2 looks pretty interesting. On number 2, the first thing you might note is I started at n equals 0. Okay, so I started at n equals 0. Usually we start at n equals 1, right, for the first term. But look what happens if I stick a 1 into our formula over here. I've got 3 times the 4/3. So I start at 4. But what I've done is I've already multiplied by the ratio once. Right? And so if you want to say start at this being the first term, then I would want to start with n equals 0, so that I would start at 3 times 1, right? The first term would be 3. So if you want this to be the first term, then we probably want to start our count at 0. Yesterday, what we did is we saw that when we were writing geometrics, or Monday maybe, when we were writing geometric series, we wrote this to the n-1 power. Okay, so there's a couple ways around this. You could write it, start at 1, go to the n-1, or sometimes we just get a little bit quicker and just say, hey, I'm gonna start at 0. So be careful you look at where we're starting. So let's see what happens. Write a few terms out, right? This is, right, terms raised to a power. But now it's saying, not only do I have 1/2 to a power, or 2/3 to a power, or 4/3 to a power for that matter, I can let x be anything. And I can ask, for which x's does this work? So we kind of really ramp things up here in number 2, because instead of looking at just one series for a particular ratio, now we're looking at infinitely many different series depending on which choice you make for x. So as soon as somebody tells you what the x is, then you can tell me which series it is, and then you can tell me what it converges to. So we might notice right away that this series is geometric. And so it's going to converge as long as our ratio is less than 1. But we don't know which series it is until somebody tells us what the ratio is. So this is a geometric series for some unyet specified ratio. And as soon as you tell me the ratio, or I tell you the ratio, then you should be able to tell me where it goes. Right? But check it out. We can write this out in longhand. This is the sort of the next thing that I would do with all of them, is I would write out a few terms. If it's in summation notation, I would write it in expanded form. If it's in expanded form, I would write a formula for it and put it in summation notation, because the two different notations are sort of helpful for figuring out what's happening. And so what's this equal to? Put in 0. X to the 0 is 1. X to the 1 is 1. X to the 2 is x squared. X cubed. X 3, 4, 5, 6, 7th. X to the nth, right? And then x to the n plus 1. And then on and on and on as n goes to infinity. Okay, so now we say, all right, well, what if you pick some value for x? Well, what if x is 0? Then life is good. Does it converge or diverge? And I can only hear Curtis, so you're going to have to say what it is.
If x is 0, then it would just be 0. So
Close. Check out where we started. X to the 0 is going to be 1. So even if x is 0, then we have to define what 0 to the 0 means. And for us, we're going to use the definition that even 0 to the 0 is 1. So you get 1 for this term, but all these turn out to be 0. So the sum is going to be 1. So it's going to converge to 1. Okay, when x is 0. It's a weird case. All right, well, what if x is 1? Does it converge or diverge?
It should diverge then, because it's just getting, oh no, it wouldn't. It would stay at 1.
Close again. Now take a 1 and stick it in for all these x's. What do you got? 1 plus 1 plus 1 plus 1 cubed, which is 1, plus 1 plus 1 plus 1 plus 1. How many 1s?
Infinitely many.
Sounds like what?
It diverges.
Diverges. Right? It gets bigger, 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 bigger forever. Now, of course, if x here is bigger than 1, like if it's 2, then you go 1 plus 2 plus 4 plus 8. Oh, that's getting big really fast. So what we're saying is, well, what if it's smaller? What if it's smaller than 1? So what if we put in a half? Then what do you have? You got a 1 plus a half plus a quarter plus an eighth plus a 16th. Looks to me like this is getting, well, the terms themselves are getting smaller, 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 smaller. So it has a chance for sure to converge, right? And so what would this be? Well, it would be a power series, right? If I put in it would be a geometric series, because if I put in a half here, I have a half to a power, which is the same as up here when I had the 4/3 to a power. And so, yes, in fact, it does. It will converge. And in fact, I think last time we said that it converged. We had a formula for the nth sum, right, of a sequence. Let's see, what was it? It was A1, 1 minus r to the n over 1 minus r. You remembering this?
So I have a question about that, because
Okay.
in some of the homework problems, I think it's the same formula, but it's a over 1 minus r.
Because there, this here is the nth partial sum. So this is the sum of the first 5, the first 10, or the first n values. The question is, what's the limit as n goes to infinity of s of n? And of course, that is the actual sum. So that would be the limit as n goes to infinity of a1, right? 1 minus r to the n over 1 minus r. So the question is, where does this go? And the answer is, well, it kind of depends on r, doesn't it? So let's think about what r could be. If r is less than 1, then what I have here is, let's say r is a half, for example. If r is a half, then I would want to have 1/2 to the nth power, which is 1 over 2 to the nth, which means this part goes to where?
0.
This would go to 0 if r is less than 1. So if r less than 1, right? That goes to 0. So what does this thing go to? 1 times a sub 1 over 1 minus r, yeah? I put a 1 on it. I think the book just called it a for the first term. And so we would say that if r is less than 1, then this goes to a1, the first term, divided by 1 minus the ratio. This is totally awesome, because as long as our ratio in this function here, and as long as when we choose x to be less than 1, in fact, the absolute value of x, because it'll just alternate. We talked about alternating series. As long as we choose our ratio less than 1, then this thing is going to converge because it's geometric. In fact, the formula that we just said will tell us where it converges. So I can write equals, right? The first term, what's the first term?
1.
1, right? So 1 over 1 minus the ratio. And what's the ratio?
1/2.
Well, yeah, and 1/2 in the example we were thinking about.
Yeah,
But what about in this problem?
a fraction.
It's got to be a fraction for sure. Maybe until
Is it just
somebody
1?
tells us, we should just write x is the ratio. Right? We don't know what it is yet because somebody hasn't said yet what it is. But we know if the ratio is less than 1, this geometric series is going to converge by our little calculation here to 1 over 1 minus the ratio. Pretty cool, huh? Let me write that down again, because that turns out to be really, really cool. What we're saying is 1 plus x squared plus x cubed plus, look, dot, 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 forever, okay? Forever is equal to 1 divided by 1 minus x. That seems like something worth memorizing, okay? Because somehow it seems like that just is really cool. And maybe that'll turn out to be really useful, right? Of course, we can write this in summation notation as well. So we could just say the sum n equals 1 to infinity of x to the nth power. Now I used n because the book does. I mean, it kind of goes back and forth. You might want to use I there, right? Because sometimes we use the n for the upper limit if we're going to a partial sum and we're stopping, right? But that's a pretty cool statement. What would have to be true for this part, this equals here? This sum equals this as long as what?
So long as x is less than 0, not 0, less than 1.
That's right, as long as the ratio is less than 1. Okay, and of course, if it's negative, then what we have is an alternating geometric series, one up and one down. And I think that we already saw that if the absolute value of the limit goes to 0, then so do the terms. I think we already saw that theorem. Okay, so that's pretty cool. In fact, that's really cool. And it's a little bit unexpected because it's sort of uncharacteristic of how you would come up with this. What we're saying is that this thing here, this infinite polynomial, this is an infinite polynomial, it goes on and on forever, has an actual finite value or a finite calculation. This turns out to be really, really, really useful. Because that means that I can say the other way around, that 1 over 1 minus x is equal to this infinite polynomial. And for this particular function, that's not that exciting, but I think we're going to see that it's going to turn out to be for some other ones. Let me prove this. Let me prove this another way. Okay, are you ready? Here comes another way to prove it. 1 over 1 minus x. We'll go the other way around, the algebra way around. What does this fraction bar mean? You remember? Means to, starts with the D.
Divide.
Yeah, to divide, right? This is 1 divided by 1 minus x. So do you remember how to do that in the good old days? We would say 1, and I'm going to turn this around if that's okay. X minus 1 plus 1, because I like my x first. That means this, doesn't it? Wait a minute, how do you do that? You can't really do long divide, can you? Well, maybe if I left it this way around, maybe it would be possible. So we'll try this. It seems weird, but let's try it anyway. It's like we'd get a fraction, right? But it's going to be like we have to add a decimal and a bunch of extra terms. All right, so how many times does 1, right? 1 go into 1? You'd say what?
Once.
Once. Yeah, 1 times this. Okay, 1 minus x. And then what do you do with these? Subtract, yes? Remember good old long division? Okay, 1 minus 1, that's 0. 0 minus a minus x, that's x, isn't it? I mean, I would be remiss if I didn't bring back, like, you know, a whole bunch of stuff that you learned from years gone by every single day in this class. All right, so what's next? How many times does this go into this?
-1 times.
-1 time. -1 time. So I'm like, ew. Don't know what to do here. Yeah? So this is starting to look a little bit weird, like not sure how to divide. I know how to long divide before I get to the remainder, but I'm struggling with how to long divide after I get to the remainder. All right, but we know one more thing, don't we? We know this for sure. If this thing is equal to this, would it be possible to check my long division? How do we check long division?
Can do the opposite and multiply.
Right on. So would it be okay if I multiplied both sides of my equation, right, by 1 minus x? You say, well, I don't know, that looks like kind of reasonable algebra. This side I get what? 1, yeah? As long as x isn't 1, right? If it's 1, then we got a problem because we're dividing by 0, okay? And then wait a minute, how do you do this? Look at what we got here. It's a dot, dot, dot. I mean, I don't know if I wouldn't even want to do that, right? That's a cubic times a, a linear term. But how would you do this? Do you remember? It's every one of these times every one of these. Are you with me? That means I got to go 1 times 1. And then I got to go 1 times x, right? And then I got to go what? 1 times x squared, yeah? And then 1 times x cubed. And then I got to keep going. Okay, and then what do I do down here? I go minus x times 1. Would it be okay if I moved it over right under here?
Mm-hmm.
Okay, and then I go minus x times x. And then I go minus x times x squared. Now way over here somewhere, I'm going to get x to the n, aren't I? And then I'm going to still keep going. So eventually I'm going to get minus x, right, times this minus. And then the one after that is going to be minus x to the n plus 1, yeah?
Mm-hmm.
And then I got to keep going. Okay, so what does that look like? That's looking pretty good, isn't it?
Looking like everything cancels except for 1.
It looks like, this is going to cancel with this, and this with this, and this with this, and this with this. It looks like everything cancels except for 1. On this side, we get 1 for sure. And on this side, it's looking like we get 1, but there's some weirdness going on. Because look, this is going to need 1 more term than this has. Yeah? So that it'll have something to cancel with. But there's good news. Because there's always going to be enough terms for this to cancel with, because it goes on forever and ever. So they will keep going and going and going and cancel. Kind of cool, huh? Okay, so what we're going to do, and I sort of jumped the gun a little bit with this section because we need to get on with it, because we're running a little short on time, is we are going to move from looking at a sequence, okay, a particular sequence, to moving to a whole set of sequences for different choices of x. So my sequence is a function of my choice for x. And then we're going to end up with kind of like polynomials that go on and on forever, that go on and on forever. And then we're going to have to learn how to deal with, how do I deal with a polynomial with infinitely many terms? And so some things that we might want to consider is, how do I do long division, right? And I mean, I got kind of stuck there. We'd have to think about that a little bit more. And how do I do the distributive property when there's infinitely many terms? And so that would be something we might have to think about a little bit. And so really, this isn't coming for a couple of more sections, like about 5. But for us, it's coming pretty quick. And so I wanted to get it on the table to let you have an opportunity to kind of start thinking about it, you know, sort of before it got here, since it's coming real fast. Now, here's the good news and the bad news. The good news is this stuff is super cool. And you could spend a lot of time thinking about it. In fact, you could take a semester-long graduate course just on this topic. Okay, so there's a lot to talk about and a lot to think about here. We're obviously not going to go that deep, right? We're going to just go a couple of days in so that you see it, so that you know what it is and get some idea of, you know, whether or not you find it to be interesting so that you could pursue it sometime in the future. Okay, but that's kind of where we are with these. But I wanted to get it on the table. What we're really interested in the last little bit of section 11.2 are problems that look like this. We want to go back now, you know, save the X for later, now that I've kind of teased you with it, and just say, okay, if n goes to infinity, what does this do? Okay, if n goes to infinity, what does this do? Okay, and if we can answer these two questions, I'd say that we did a good job on section 11.2. And then in a few days, maybe we'll try to put the X back in and explore it a little bit more. All right, you ready? 3 and 4? Okay, here comes 3. What I would do on 3, what I would do on all of them is I would go quickly over to Desmos. Now it's all set up, right? This is always the same. I'm going to move it up there. This is just graphing the points. This is just graphing the sum. Okay, the sum is always the same, the formula for the sum. So all I really need to change is our formula for the sequence. And this one was 1 over n times n plus 1. Okay, now the question is, what's it doing, right? And it looks to me like, right, looks to me like going to 0. Yeah, looks to me like the sums are going to 0. Where are the terms? I don't even see them, they're green. Well, we might have to stretch this out a little bit so I can see them a little better. All right, how about 0 to 1? Okay, so remember the terms are green, the sums are red. The terms look like they're going to 0. Well, for sure they're going to 0. Look at this, what's going on? N gets bigger. What's the limit of this sequence as n gets bigger? N's in the denominator, goes to 0. Are we okay?
I have a question.
Sure.
Isn't the sum supposed to be a of I?
A of I, yeah. Where is it? Up there. Probably a good catch. So how did you catch that?
I was looking at it, and if it's counting by I equals 1 and going to n, not going to be a of n.
Ah, remember we talked about the fact that that if you're going to use n as the independent variable here, right, as the upper limit, right, then you can't use it as the index as well. So it's pretty easy to get that sort of mixed up, right, especially if you're zooming along in a hurry. So pay attention to that, right? Otherwise you'll mess it up like I did. What's another way that you could have caught it?
Getting the wrong answer.
Yeah, getting the wrong answer. Get a red X, right, in WebAssign. Okay, that's one way. Okay, but think about the sum. What are we doing with these terms here? You want me to write a few out? I'm going to write a few out over here.
We're adding up a bunch of fractions.
Yes, we are. So does that sound like it adds up to 0?
No.
No, right? That doesn't sound like it adds up to, so I'm going to write the partial sum is I equals 1 to n of the terms, right? So, whoops. I equals 1 to n of the terms, which in our case is going to be the sum I equals 1 to n of, what was our formula? 1 over n times n plus 1. So what should we do? We should write a few out, right? So that's 1 over 1 times 2. And then we've got 1 over 2 times 3. And then we got 1 over 3 times 4. And then we got 1 over 4 times 5. I think leaving them without multiplying them together makes it clear about what's happening. Right? So if you multiply them together and you got 2, 6, 12, 20, those numbers don't really tell you as much about what's happening as if you leave them unmultiplied. If you leave them factored, I think it's a little bit easier to see. Okay, so what do I got? A half plus a sixth plus a 12th plus a 20th. I'm adding up a bunch of little fractions. I'm pretty sure it doesn't go to 0, yeah?
Yeah.
So that would have been a pretty good catch. Okay, so what does it go to? Well, I don't know, it's a half plus a sixth. 1/2 plus a sixth is already 4/6, right? That's already up to 2/3. Are you with me?
Yeah.
Okay, so the second one is already 2/3. So then when I add 1/12 to it, now I'm up to 3/4. I mean, this is getting bigger, isn't it? It's going to a number and it looks like it's going to what?
1.
It looks like it's going to 1. So generally speaking, I would say that Desmos is going to help you to get your head wrapped around the problem. You can see what's going on, okay? But you got to be a little careful. Sometimes your error could be what you typed into Desmos itself. Okay, so I would call the part that we just did just getting familiar with the problem, getting your head wrapped around what's happening, seeing it, talking about it, thinking about it a little bit. So sometimes we're going to use Desmos to see what's happening. And sometimes we're going to use what our knowledge is about what's happening to help us get Desmos right. But if you look at it in two different ways, sort of algebraically, using notation, and in Desmos geometrically, you should be able to get those two things to match so that things are making sense to you. And you catch little errors like we're adding up a sub n, yeah, the nth term. Okay, you with me? Are we good? I think we're good. And at this point, I would say I think it's going to 1. So the question is, how do I prove it? Okay, I mean, that's really the question. How do I prove this is going to 1? And if I come back over here, and let me get rid of this. If I come back over here now, and I look at this, I'm saying this is not a geometric series. In a geometric series, I take the previous term, right, and I multiply it by a number, and then I multiply it by that number again and again and again. So I can't get from a half to a sixth. To get from a half to a sixth, I'll have to multiply by 3. But then to get to from a sixth to a 12th, right, I'd have to multiply by 2. And from a 12th to a 20th, something different. There's no common ratio here. And so this is not a geometric series. So we can't do the stuff we did on Monday. So we're going to have to do something else. Okay, so what do we do? And the answer is, what do you got, Shane?
Okay, so if you pull out a fraction, specifically the you can pull out 1/2 from the first two terms.
Okay.
And then you can pull out 1/3.
Okay.
And then a 4th, then a 5th, and then
Yeah.
after that a 6th and a 7th and an 8th and a 9th.
Okay.
This looks like the ratio changes. There's no fixed ratio this time. It's like a separate function.
Yes, it is. In fact, that's why it's not geometric. For geometric, it has to be a fixed ratio, and here the ratio is changing. So let's do what you just said. What you want to do is get this 2 out of here. You want to pull the 2 away from the 3 and the 1, and here you want to pull the 3 away from the 4 and the 2. You want to split this up. Okay, so what will we do? Split this up. So let's see if we can do it. I want something over n, right? And then I want something over n plus 1. Can I break it up into two pieces? Can I split my denominator up? Can I decompose it? Sounds like partial fraction decomposition to me. Good thing we know how to do that. All right, so I have to find an A and a B that make this true. So how do we do it? Do you remember? You got to go this times this, this times this. That's the common denominator. So I get A times the n plus 1 plus B times the n would have to be the numerator. So this times this times this has to be the 1. And this times this is the denominator. The denominators are the same. Okay, so what's that? That's an plus bn, right? Plus a has to be 1. So a plus b, right, times n plus a has to be 1. So I'm thinking a plus b would have to be 0 since there aren't any n's over there. A would have to be 1, which means since a is 1, plug that in here. B would have to be minus 1. So A is 1 and B is minus 1. That's what I'm thinking. On a couple of your papers, maybe even one of your papers, I don't remember, but somebody in class, if you do some partial fraction decomposition, you got to at least show me that you split it, okay? And you got to give me some indication that you can do that. So you got to show a little bit of work there. You can't just like write the answer down without kind of giving me a little bit of the details. No, you don't have to write the system of equations and solve the system by substitution, especially if it's 4 equations, 4 unknowns. You can just write RREF. I did RREF on my calculator, but you have to give me a little bit of this work, okay? And I think that that'll be true in your other classes as you move down the road. Okay, so I'm claiming our sum, I equals 1 to n. A was 1, so I get 1 over n, and then B is minus, so I get minus 1 over n plus 1. All right, so the question is, does this help? And the answer is yes, because a while ago, we learned some things about sums, like the sum of a sum is the sum of the sums. In other words, I can add all these up, then I can add all these up, right? And then I can combine them. We also learned that a constant, the sum of a constant times a sum is the constant times the sum. In other words, there's a bunch of rules for sums, aren't there? And I think those rules, we investigated them a little while ago when we were talking about Riemann sums. And I think that Stuart puts them back up in front of you again on in the book. He reminds you of what they are, but he doesn't spend a lot of time. He doesn't spend a lot of time proving them. So here they are. Okay, the sum of a constant times a sequence is a constant times the sum of the series, right? The sum of two sequences, when I combine the terms ahead of time, is the same as summing up the A's and then summing up the B's. And the same for the difference. So this gave you a few rules for series. Okay, it gave you a few of the rules for series. And then it said there's other ones, but it didn't go into them in detail here. So if we need them, we'll have to go find them in the future. But what I'm thinking is these seem pretty straightforward. My question to you would be, how do we prove it? How do we prove any of these statements? And I think the general trick, I don't know if my thing's going to cooperate. It doesn't like focusing on the book. It's too small. The general trick for proving any of these kind of statements is to write out the sum in expanded form. So let's see if I can prove one of these with you. So stop this problem for a second. You have to take an aside. And so what if I want to prove that the sum, and of course, he keeps going back and forth, n and I, which is why I keep getting it confused. CA sub n is equal to C times the sum, n equals 1 to infinity of a sub n. In other words, I can factor out the C. How do I know I can factor out the C? Okay, what you would do is you'd make this side look like that side, and do that by expanding this. So this is equal to, going down this way, C times A1 plus C times A2 when n is 2, plus C times A3 when n is 3, plus dot, 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 right? This goes on forever. Now that's the weird part, I guess, because of the, I'm gonna have to learn how to deal with something that goes on forever. And it takes a little while to do that. I mean, we're just scratching the surface now, getting some experience. But like I said, you can spend, a whole semester just dealing with these things. It looks to me like every one of these terms has a C in it. So it looks like I could factor the C out of all of them. In which case I get what's on the right-hand side, right? C times the sum, n equals 1 to infinity of a sub n. The question is, and this is a very subtle question for you graduate math student types, okay? Do you see what we did right here? We factored out the C. Well, I know I can factor a C out of finitely many terms. Okay, that's called the, factoring. That's a distributive property backwards. But how do I know that the distributive property works for infinitely many terms? How do I know I can pull a C out if this goes on and on and on and on and on and on forever? And that's a very good question, right? One that's certainly worth some more investigation. Anytime you have a dot, 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 I suspect that the answer is going to involve a limit. You're going to have to somehow write this in terms of a limit and then prove something about what happens as the limit gets bigger and bigger and bigger and bigger. Okay, we're going to take this on faith because this seems like a pretty logical argument. It seems like the distributive property works for finitely many terms. So why shouldn't it work for infinitely many terms? And the question is, well, I guess it does since they gave it to us, but we haven't proved that yet. Okay, so that might be worth a little bit more investigating. Okay, ready to go back? Let's finish this problem off. I'm claiming that we can use what we just didn't prove, right? Right here. So we're going to use it for a while and see if it's given us the right answer. But you would have to say, well, all right, you talked about the proof, but you haven't really done it yet. Of course, we need to save something for the future, right? So we're going to save it. So I'm going to say this is the sum I equals 1 to n of 1 over n, right? Minus the sum I equals 1 to n. Am I messing this up again? We wanted the infinite one. How come you guys keep letting me do this? Okay, that's fine. This was the partial sum. But then these should be i's, shouldn't they? Good grief. All right. I and I plus 1. And then down here we get I and 1 over I plus 1. Are we okay with that? The sum of the sum, or in this case, the sum of the difference is the difference of the sums? Okay, so now what? So if we only knew where this goes, right, then I would think that we would know sort of where this goes, yeah? But I don't know this because this is problem number 4. This is problem number 4. We got to do problem number 4 before we can solve this. But there's still good news. Okay, here comes the good news. Let's write out a few of these. Not like this, okay, but rather using this up here. All right, so what about when I is 1? I get 1 over 1, right? Minus 1 over 2. True? Okay, then I get plus. Now I is 2. So I get 1 over 2 minus 1 over 3. Now I get 1 over 3 minus 1 over 4. And then, look, it just keeps going, doesn't it? Well, check this out. This is a minus half. This is a plus half. This is a minus 3. This is a plus, a minus third plus a third. So this is a minus a fourth and a plus a fourth. So eventually I'm going to get a 1 over n and a 1 over n plus 1, yeah? And the one before it is going to be the 1 over n minus 1 minus 1 over n. So this one's going to cancel with that one. And this one's going to cancel with the one before it. So what's left?
Just 1.
1 minus 1. Oh, Stuart.
I wanted to cancel.
Crazy Stuart is driving me nuts out here, yeah? Because all those n's should be i's in our notation that we chose. I think I'm just going to choose to use n's from now on because I keep writing them down. Would that be okay?
Yeah.
Mm-hmm.
Good, because I can't seem to write them correctly. Okay, so this is what it goes to. Yeah, as n goes to infinity. Well, check out what happens now. What happens when n goes to infinity?
That number goes to 0.
That goes to 0 because now we have the limit as n goes to infinity. This goes to 0. The whole answer goes to 1. And life is good. Because in Desmos, after we played around with the index for a little while, we noticed that it went to 1. And now that we did this, we fumbled around with this for a little while, and this is also going to 1. Well, that's pretty good news. Right? I'm feeling more confident that it's going to 1. Now, was this an all cleaned up, nice, polished argument? No, we were just fumbling around, thinking about stuff. And that's going to take some investigating. It's going to take some kind of start and stopping. It might take us needing to get familiar with the notation. It might include a few mistakes here and there that we have to, go back and correct. And of course, the more that we do with these, the more fluent we'll get, the faster we'll get. Okay, but that's a pretty good proof. I think that proof worked really good. So what do we call this? I don't know, getting lucky, I guess. We had a series, okay? We had a series. By the way, this one's wrong, right? Because this should be n equals 1 to infinity. There, let's just write it that way so that I don't have to change my n's to i's. We had one that looked like this. We said, well, if this was only geometric, we could use the stuff we learned earlier to finish this off. We know where the geometric ones are going. But then we realized that the ratio is not the same every time. So it's not geometric. But looking in Desmos, we still think that this is going to a number. We still think this converges. And there's a pretty good chance that it does because, of course, the terms themselves, these terms, the 1/2, 1/6, 1/12, they're going to 0. So I'm adding up something smaller, 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 smaller pieces. Sounds like that might go to a number. And it looks in Desmos like it goes to 1. So now the problem is, how do I prove it? And the answer is, there's no answer. There's no formula for these. Like when we were doing integrals, they sort of fell really nicely into categories. Use parts, use partial fraction decomposition, use trig sub. They fell into really nice little categories. It turns out that there are some nice categories for these series. If it's geometric, for example, then we know what it's doing. Okay. I might mention another category too. If it's a power series, we know what it's doing. So I'll go back and look at those. Those are the two categories that we recognize. But if it's not either one of those, then there's not really a particular strategy that we would use. You just have to kind of fumble around and try stuff. So what will we try? Well, I don't know. This is put together. So maybe we try ripping it apart using partial fraction decomposition. Yeah, and when we did, look at what happened. We were able to get the rest of the problem to fall out real nice. Now, does that mean that partial fraction decomposition is going to work all the time? No, it's hardly ever going to work. I mean, it's going to work on one. If I give you like a 1 over n plus 1 times n minus 3, well, it's going to work on that one. Okay, because it's going to look a lot like this one, right? But for the most part, each one of these is going to require that you sort of fumble around with it individually and find some kind of trick or strategy that works for each problem. I mean, it's not quite that bad because there are several sections that we're going to take a look at about how we might do this. But in general, finding the sum of a series is not an easy task. Okay, it's a semester of graduate school. That's what that is. And so I guess the moral of the story is at some point, we just stop. And we're about there now. We stop trying to find what this goes to because it's just too hard to figure out what it goes to. And we just ask, does it go anywhere? In other words, we're content with deciding if this series converges or diverges. And even though we decide that it converges, it just becomes too difficult to figure out what it converges to. So we abandon that and we don't try. We just decide, does it converge or diverge? Okay, stop right there. Or maybe not stop right there. We say, well, if it converges, is it geometric? Because if it's geometric, we know what it converges to. If it's not geometric, then maybe we can do a couple of cool tricks like we did on this one. But for the most part, we're just going to say, I don't know what it converges to. If you really need to figure it out, then we need to take some more math classes. Okay? Is that making sense? This is a weird place in the book. It's always a weird place for me to get to because we've been talking about this series converging and figuring out what the limit is. And now what we're going to do is we're going to say, I'm just going to have to be content figuring out whether or not it converges or diverges, because figuring out what it converges or diverges to turns out to be really challenging, in fact, and really interesting. So well worth you spending some more time thinking about it as you go down the road. This one has a name. I think this is called a telescoping series. And you would get it by partial fraction decomposition. But in general, we just essentially we got lucky. If it's not geometric, then it turns out that they're pretty hard. Let me look at the last one. Let me put it up here because I mentioned it. It was a power series. It looks like this. If you have a series, let's see. If you have a series that looks something like this, we have a series of a ratio, right, to a power. Okay, so if we have ratios to powers, in fact, we had this kind, right? A first term times a ratio to a power. We even wrote it to the n minus 1. So n equals 1 to infinity. This is what we called geometric. In fact, this morning we said that it converges to the sum, right, is equal to 1 over 1 minus the ratio, right, when the ratio is less than 1. So not only do geometric ones converge, but we know what they converge to. Beautiful. Here's another kind. The sum I equals 1 to infinity of what do I want to write here? How do I want to write this? I want to write 1 over n. Let me see what notation he uses. I don't want to mess it up later. Let me see what notation he uses. Maybe I'm just jumping the gun a little bit too much here. Okay, maybe I'll just write it like this. Well, all right, I'm gonna write to the p. Okay, where p is a number. So specifically what I'm thinking about is, what if you had something that looked like this, 1 over n squared, like this? Huh? In other words, now I'm adding up 1 plus 1/4 plus 1/9, right? Plus 1/16. Converge or diverge? What do you think? Okay. We don't have enough experience yet. Yeah, converges.
Yeah, it should converge because the ratio, or the actual number of the ratio, is getting smaller and smaller.
These are getting smaller and smaller, so it has a chance to converge, right? And these are getting small really fast, aren't they? So the question is, for what values of p, right? So when p is bigger than 1, it turns out that these all converge. And we've already looked at a bunch of these, but maybe I'm jumping the gun a little bit to look at the general case. I guess they're coming here pretty soon anyway. Right? I think we already looked at the sum of the squares, yes? We looked at those. But the one I want to look at next is this one. What does this do? So remember, this is always a race. These terms that I'm adding up are getting smaller, 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 but my sum is getting bigger, 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 bigger. So if the terms are getting smaller fast enough, essentially I'm adding on infinitely many infinitely small things. And if those infinitely small things get really, really small faster than I'm adding them up, then I basically am adding on nothing. On the other hand, that would be this case. On the other hand, even though these things are getting smaller, I'm adding them up faster than they're getting smaller. So I'm still adding up things that still have some substance to them, which means my sum is getting bigger and bigger and bigger and bigger. We could see an example of that if I just wrote this one down. Right? Where does that go? You'd say, well, that doesn't have any chance because the terms themselves are now getting bigger and bigger and bigger, and I'm adding on something, I'm adding on more and more bigger and bigger things. Are you with me? So this has no chance, right? This, I'm pretty sure, does this. And the question is, what about this one in the middle? And so that's our last little investigation. And I'm starting to run out of time a little bit here. And so let's just take a look at them real quick. Let's take a look at them real quick. What do we want to add up? What if we want to add up the terms? Well, then you can see there they go, shooting off to infinity real fast, yeah? No chance to converge. Okay, what if we want to add up, what if we want to add up 1 plus a half plus a third plus a fourth plus a fifth? Then I've got 1 over n. Looks to me like the terms, they're getting smaller and smaller. That's good, because if the terms aren't getting smaller and smaller, then there's no chance for it to converge. But what does it look like is happening, right, with my sum? starting to bend.
Yeah.
The question is it going to bend and level off? Or is it not going to end up bending fast enough and just keep on going up? You know, maybe we could put a few more terms in here. There's 1,000 of them, right? Bending, still bending over, and infinity is a long way to go. So by the time I get to infinity, would it have bent enough? I don't know. Let's try 10,000. Oops, try 10,000. How come it won't 10,000? Because Desmos ran out of memory. Huh? I'm getting a little warning over here. So maybe I can try 5,000. Will it go to 5,000? No. Will it go to 3,000? Yep. Okay, so what's happening? By 3,000, it still seems to be bending. I mean, are you kind of feel like you're looking at the COVID curve here? This is like, is it ever going to, this is us right here on the COVID curve, right? Is it ever going to start bending? You know, that's what we're kind of doing every day, right? This is not what we want the COVID curve to do, right? This means it keeps going up and up and up and up and up forever. This seems to be still going up. Slowly, we've slowed the spread, but it's still going up, which means we're all getting it eventually. What do we want? We want it to level off and actually stop going up, because that means we're not getting more cases. Let's make the bottom get smaller a little bit faster. What if I go by the squares down here? Oh boy. Okay, so I'll zoom way in on this. Of course, the terms, they're going to 0. And the terms are going to 0 even faster than they were before. Do we agree? So it's got a chance to converge. Sorry, I'm talking, you got to look at the side of me because when I've got Desmos up, you're way over here on the side of my screen. So to see you guys, I got to look over here instead of looking at the camera. All right, now look at the sums. Sums are definitely bending over, right? There they go. The question is, well, right there, it looks like they're still going up, but are they going to kind of level off? Wow, it looks like they're leveling off, but it's pretty imperceptible, right? Do I know they're leveling off, or are they just creeping up ever so little bit? I'm going to argue that these level off and that they never get, they have a sum. And what's the sum going to be? It's going to be somewhere around, what, 1.7 or so? But I'm going to argue, in fact, you want to know what this number is? This number, I think that number is pi over 6. Nope. I think that number is, I'm gonna have to think, I think that number is pi squared over 6. Huh. Does it look like maybe these guys could be coming up, getting closer to pi squared over 6? You say, well, yeah, it could be. It could be any number in there, right? Do you remember when I said that it's sometimes hard to figure out what it goes to? Showing that this sum goes to pi squared over 6, not easy. Well, okay, easy once you put a few more pieces in place. So we're not going to worry too much about what it goes to for now. We're mostly going to worry about, is it going somewhere? Is this converging or not? Okay, and I'm going to argue just by looking in Desmos, looks like it's got a better chance than 1 over n, because 1 over n seemed like it was still angling up a little bit. But in Desmos, it's hard to tell. So the question is, what do we do when it's too close to tell, right, by looking in Desmos? To me, this looks like it's flattening. To me, this one, right, this one looks like it's not flattening. Looks like it's still creeping up. So now, this is a pretty easy question, though. You'll like this question. What do you think that one's doing? I mean, if 1 over n squared is flattening, what do you think about this one? I'm thinking that one definitely is flattening, wouldn't you say?
Yeah.
The terms are getting smaller, right? Even faster than they were before. So if it's going to converge for n squared, then I suspect it's going to converge for n cubed. Why? Because when I add up the terms of n squared, the terms of n cubed are all smaller. Let me draw that over here. I'm trying to do like 6 sections in one day, if this feels a little bit like I'm jumping all around, yeah? It's trying to do the highlights, but sometimes it's hard to fill them all in. All right, so let's look at 1 over n squared. And let's look at 1 over n cubed. So let's write a few out. So I get 1 plus a quarter plus a ninth plus a 16th plus a 25th. Yeah, plus dot, dot, dot. And down here I get what? 1 plus an 8th plus a 27th plus an 81st. Is that right? No. 256 maybe? Wait, 64 maybe? 4 cubed? Am I in the right place? 64, I think.
4 cubed. Yeah.
5
Yeah.
cubed, 125. I better stop now because I need a calculator. Look at what's happening. This term is smaller than this one. Do we agree? And this term, 127th, is smaller than a ninth. And a 64th is smaller than a 16th. And 125th is smaller than a 25th. So as I keep going, all the terms down here are going to be smaller than all the terms up here after the 1. Seem like a reasonable argument? So if I add up all these terms and I get a number, then when I add up all these terms, I'm feeling like I'm also going to have to get a number, right? In other words, if the top one converges, the bottom one has to converge also. Because here I'm adding up bigger stuff that actually goes to a limit. So if I add up smaller stuff, it should certainly go to a limit. Now it might be a different limit, right? But it's definitely going to converge. If this one converges, then when I add up smaller stuff, it's definitely going to converge. Is that making sense?
Hmm.
The question is, what happens on this one? And we're saying on that one, I'm thinking that one just keeps creeping up bigger and bigger. It doesn't converge. In fact, this series has a name. This is called the harmonic series. And the harmonic series diverges. But these series, which we're going to call power series, because it's numbers to powers, yeah? They all converge for P greater than 1, meaning the sum n equals 1 to infinity of 1 over n to the p. Okay, for p greater than 1, those all converge. So you can, I don't know, write this down, remember it. The harmonic series diverges, the power series, they all converge. The geometric series, they all converge, and we know what they converge to. Some series are telescoping, and you can get away with little partial fractions on it. Some we're going to have to investigate a little bit more carefully. And I don't think we're done with this yet, right? Because we looked at it, we guessed by looking at Desmos, but we haven't really done a formal proof that either one of these things are true. I kind of took you through an argument that would say, if it works for squareds, then it probably is going to work for cubes. And then it's probably going to work for fourth powers and fifth powers and sixth powers, yeah? because these terms are smaller than those. And it makes sense if these add up to a number, then these should. Okay, but none of that's a real formal proof yet. And so we want to spend a little bit more time thinking about how do I prove any of these things that I've been talking about, right? So we're going to need some more days.
You take the
Okay.
derivative of a sum?
Ooh, that's a very good question. And the answer is yes, but maybe we'd have to talk about what that means.
Yeah,
Because certainly, go ahead.
because that would have some massive applications. Like if you, instead of taking the limit and doing all this stuff,
Yeah,
you literally just do the first derivative test, find out where the slope is 0, done.
yeah, that would be good. Unfortunately, in this case, it wouldn't be 0, but it would certainly tell us if the terms are increasing or decreasing. And it
Yeah.
would also tell us how fast they're increasing and decreasing. So I think you're onto something there. Yeah, you're definitely onto something. You're about 9 sections ahead of where we are, but we're on our way. So I'm gonna let you keep thinking about that. And let me just look at my notes and see if there's anything else I can squeeze in today. I think that we've pretty much done it though. The rest of my notes just have a bunch of examples of more series for you to investigate. So like homework problems for you to try. I'm going to, I'll tell you what, I will do this, prove this. Okay, and I'll send it to you because we're out of time today. I'm going to see if I can make a stronger argument than it looks like it in Desmos. So let me write up an argument for that and I'll send it to you. And then you can read it and see if that is more convincing than it looks like it does in Desmos. Yeah. And remember, that's what the proof really is. The proof is, did you convince your audience, that you're right? And if they all agree, then you proved it, right? And so you never really prove it because somebody might come along that's really skeptical and say, well, what about this? Did you think about this? And then you might have to, be more rigorous in your argument. But I think I can come up with something stronger than it looks like it in Desmos. And so let me see if I can put that together and send it to you since we're running out of time. And then next, where are we? We're to Friday. So on Friday, what I'd like to do is I would like to go a little bit more in depth than what we did today, but we're not going to be able to really dig into this section because we would need to look at section 3, 4, 5, 6, 7, right? So 3, 4, that's 5 sections worth of more investigating. We're going to do like one more day of investigating on this. And then I'm just going to have to leave the rest for another class a little further down the road. Katie.
Sorry. So that means we're still working on 11.2 on Friday?
We're working on, no, I think this is it. Other than this little proof that I'm going to send you, I think we've got 11.2 done.
Okay.
So you should be able to do all the homework from 11.2. On Friday, I want to look at 11.3. Okay, I already set the stage for 11.3 and 11.4. And I think that Shane just gave us a big hint about how we might think about this too. And so I want to do sort of an overview, it's going to have to be a little quick because usually, that's 2 sections in one day. But I would like to look at 11.3 and 4, and then I'm just going to have to let the rest go. Okay, 5, 6, and 7, I'm just going to have to let them go. So if you have nothing else to do and you want to investigate that on your own, you can, and you can send me questions about it. You won't be behind like anybody in Calc 3 because you didn't get that far. Okay, I mean, there will be some students who will have looked at it a little bit more than you, but there won't be any students that are like have mastered it yet. Okay, no one has enough time in Calc 2 to do a really good job with this. because really this is like a whole class that takes a whole semester long. So if you've got some experience with it, you'll be ready to move on down the road. So don't feel like you got sort of shortchanged due to COVID or anything like that. I think we've done a pretty good job with this. But you might notice that I was going to try to do a few problems from 11.7, but I just got rid of that homework assignment. Let's get to Friday and we'll see how much of 11.3 and 4 that we can do. If it turns out that we just don't feel like we want to even look at any of those problems, maybe we'll just skip those homework assignments, or maybe I'll cut them down or something like that. But you should be able to finish up 11.2 now without any trouble. And then on Friday, we'll just see where we get. Does that sound okay?
Mm-hmm.
Okay, you guys. Well, have a good couple of days. If you want to come back and chat during office hours, you can. Otherwise, have good luck with working these out, and I will see you on Friday.
All right. Thanks. See you then.
Okay. Bye-bye.
Bye.
There's not a quiz Friday, is there?
No. Oh, well, sort of. I've got a little take-home, a few take-home problems that I'm going to give you. I was thinking that we could get to them by Friday, but it might be Monday. I just got it kind of set up there in Canvas, but it's not going to be like an official quiz. It'll just be like a take-home quiz with a few extra problems. So I was hoping maybe Friday. We'll see how far we get. Okay, but don't worry about it. You'll have plenty of time to do it, like the whole weekend or into next week.
Okay, thank you.
You bet.